We have made it to the end of polynomials. This is lesson 9. Remember, this is just the review lesson and it includes all the key points from the other lessons. It doesn't include every slide or every example, so if there's anything you're still unsure of, look back to the individual lessons and have fun. Here we go. So, what are polynomials? Well, expressions like this, where you have x to the power of 5, 4, 3, 2, 1, 0, are polynomials. This is a polynomial of degree 5 because 5 is the highest power. You don't have to include all the powers. For example, this here, this expression is also a polynomial, and this one would be a polynomial of degree 12. Because it's the highest power. You could also have x minus 3 bracket 2x plus 5. That would also be a polynomial because if you multiply out the brackets, ba-dinky dinky dinky donk, you get this. And it's a polynomial of degree 2. Again, because 2 is the highest power. Note, for every single polynomial we have here, all the powers are in descending order, and that's really how you should write them. Coefficients. What is a coefficient? Well, that is a number in front of a certain variable. So in here, the coefficient of x cubed is negative 7. In here, the coefficient of x to the power of 5 is 9. It's the number in front of x to the power of 5. Roots as well. What are roots? Well, roots are the values of x that make the function equal to 0. In other words, it's where the graph crosses. If you were to graph your function, it's where it crosses the x-axis. After that, we looked at some of the previous knowledge because we have dealt with polynomials in our past, long time ago. We factorized polynomials, so we can factorize the likes of this. We can look for highest common factor. We could also look for difference of two squares, and we can factorize trinomials. So we have dealt with polynomials in our past, even though we haven't really realized it. Finding roots. We've also found roots of polynomials because we can factorize to find the values of x that would make this expression equal to 0. And if you do that, here we've got 2 and negative 2, so really that's the roots. If you graphed it, you know this quadratic here would cross the x-axis at 2 and negative 2. And finally, we can evaluate polynomials. So if we have f of x, we could work out f of 2, for example, by replacing x with 2. So that was the previous knowledge showing you that we have already dealt with some of the polynomials chapter. After that, we moved on to evaluating the likes of g of x. Here it equals this polynomial, and we could work out the g of 2 in two different ways. Either we could replace x with 2, so we're using substitution, woohoo, or we could use what's known as the nested form. And the nested form, a way of setting that out, is using this L shape here. And if we want the f of 2 in this quadratic, in this polynomial, we can put a 2 here and then work our way along. Remember, you multiply by the 2 and you add the columns. Because we're getting a 1 here, it means the f of 2 is going to be 1. Example 3 with that one, I'm not doing example 2. Example 3 was slightly different, really, because I had 0x squared. So you've got to make sure that we've got x to the power of 4, 3, 2, 1, and 0, but we don't have an x squared, but you still need to include that when you're setting it out like this. So you would write down it's 0. So make sure if there's an x term missing, like an x squared term missing, you include a 0 there. You do still need that. After that, we looked at synthetic division, and we were talking about normal basic division. And if you have a division such as this, then there are different parts, and you need to know these words. The remainder, we've been dealing with that since primary school. We've been dealing with remainders, but this number here is known as the quotient, and the thing you're dividing by is the divisor. You can also reverse this dividing calculation, and you could write it in this form where you've got the original number equals the divisor times the quotient plus the remainder. And sometimes when we apply that to polynomials, we're asked to write it in this form, just for fun. So, how does that get harder? Well, if you divide this polynomial by x minus 2, we'd have to use this synthetic division. And for synthetic division, that uses the nested form. It sets the divisor equal to 0, and that gives us the value to the left of that vertical line. So the steps for using your synthetic division: first of all, draw the L shape. write down the coefficients, set the divisor to 0 to find the value left of the vertical line, work your way through that by dividing, and then you can read off the quotient and the remainder. Just remember your polynomial, if you write that, it's very similar to what we did with the numbers there, but the way you do it for a polynomial is you would have x minus that value to the left of the vertical line that you found in step 2, times by the quotient plus the remainder. When we divide f of x by x minus h, the remainder is f of h. So if you were dividing by x minus 2, the remainder would be the f of 2. Some examples of that, if we were dividing this polynomial by x minus 2, first of all set the divisor equal to 0. Arrange that so you get x equals, x would be 2, and that's the number that goes to the left of this line. Work your way along, so add the columns, multiply by 2, multiply across, so that would give you 10, then 12, 24, and so on. Because you get 62, it means there is a remainder of 62. Or, in other words, you could say that f of 2 is 62. Really, that's what the remainder is. For the quotient, well, all these numbers are the coefficients of the quotient. So if here in your original polynomial you have a polynomial of degree 3, 3 is the highest power, take one off that and you'd have an x squared. So that then would be 5x squared plus 12x plus 32. If you were asked for it, if you did rewrite that polynomial, you could say that would be x minus the value to the left of the vertical line. In this case it's 2, so it's x minus 2 times by that quotient, and again plus the remainder. We had more examples of that. This example here, it wasn't any more complicated, it was just worded, but don't let it confuse you. It's still asking for the same form as before. It's x minus something times by the quotient plus the remainder. So there's nothing different to that. This example here though, we're dividing by 2x minus 1, so you've got to be careful if you're not given an x plus or minus something. If here it's 2x plus or minus. So for that one, do the same thing, set that divisor equal to 0, rearrange it so you get x, that goes to the left of the vertical line. Once you work your way along, then you end up with 2. But if you have to rewrite that, which you're asked for in this question, then you remember you do x minus the value to the left of the vertical line. So in this case, it's going to be x minus half times by this quotient plus that remainder. So don't just write it as 2x minus 1 times something. It's always x minus that number to the left of the vertical line. After that, we looked at factor theorem. What are factors? Well, a factor is a number that divides a given number exactly, and it does not leave a remainder. You get a remainder of 0. For example, 12, you can divide it by 1, and 12, and 2, and 6, and 3, and 4, and the remainder is always 0. So they would all be factors. You cannot divide it by the likes of 9. It doesn't work because there's a remainder. You'd have a remainder of 3. In the last lesson, so just before this, we were dividing a polynomial by x minus h. X minus h, it turns out to be a factor of that polynomial if the remainder that you get on the end in that L shape when you use your synthetic division turns out to be 0. If there's a remainder of 0, then it's a factor, which is what it's saying here. If f of h is 0, then x minus h, x minus that number to the left of the vertical line, would be a factor. We tried some examples with that. So this one will show that x minus 4 is a factor of this polynomial. How do we know it's a factor? Well, you divide it. So divide by x minus 4, set it equal to 0, find out what x is, put the 4 here, work your way along, and we get 0 here. If it's 0, then it means it's a factor. And that is how we do those questions. We tried some other examples. This one here, it didn't tell us any factors or any roots or anything like that. It just said factorize this fully. How do you factorize this fully? Well, first of all, you need to work out what number is going to give you a remainder of 0, or what number when you substitute it in here will give you 0. So substitute in 1, a negative 1, 2, a negative 2, and work out what gives you 0. Here, if you try 1, if you work your way along, you get negative 36. It doesn't work. You need 0 in order to get a factor. If you sub in negative 1, you get 16. Still doesn't work. If you sub in 2, remember there's 2 ways to do it. You can either use your synthetic division, setting it out like this, or you could just sub it in. If we sub in 2, we get negative 35. Negative 2 gives us 45. However, if you sub in 3, then you're going to get this remainder of 0, which means then that x minus the number to the left of the vertical line, x minus 3, is going to be a factor. Therefore, we can say that this polynomial is x minus 3 times, and the way you get the coefficients, look at the bottom line here. This is the coefficients of the other bracket. So because we've got an x cubed, that becomes 2x squared plus 11x plus 5, and you can factorize that just the way you have been doing for years. So you get x add 5, 2x plus 1. You can obviously write these out in any order you like. Example 3, show that 3x minus 2 is a factor. That was very similar. Again, you set that equal to 0, arrange it so you get x. X is 2/3, put that to the left of the vertical line, work your way along and you get 0. Because you've got 0, it doesn't mean that 3x minus 2 is a factor. It means that x minus this number to the left of the vertical line is a factor. So you would say x minus the 2/3 is a factor. Therefore, you can set it up so you get the coefficients of this part down here, just in red. But then, a lot of the time, what you can do is you can take out, for example, 3 as a common factor, multiply this bracket by 3, and we get that 3x minus 2, which is showing that that would be a factor. After that, we were solving equations. This was really just taking that last lesson one step further, and we set the polynomial equal to 0. So now we have to find the values of x. In other words, we have to find the roots. The roots are the values of x that make the polynomial equal to 0. In other words, if you graphed it, it's the places that the graph would cross the x-axis. So with this example here, we had to first of all factorize it. We know x minus 3 is a factor, so divide this by x minus 3. And this is what we get. We get 0 here, which confirms it is definitely a factor. Therefore, we can say it's x minus 3 times, and we'd have 1x squared minus 1x minus 2. Factorize this bit fully, and we get x take 2, x plus 1. This bit is new because we are just then solving that. This is what we did in the last lesson, factorizing. This new lesson was solving it. So set it equal to 0, you were told that in the question, and then if it was equal to 0, either this bracket equals 0, this bracket equals 0, or this bracket equals 0, solve for x, and you get the 3 values, so you get the 3 roots. Remember, these would be the places that the graph would cross the x-axis, as you can see right here with these big funky green dots. Why? With this example here, we had to solve that. This polynomial equals 0. Again, you're not given a factor or a root, so we need to evaluate f of 1, f of negative 1, f of 2, f of negative 2. Sub in 1, negative 1, 2, negative 2 in here and see what does give you 0. These numbers don't work, but 3 does. If you sub in 3, you will get 0. Set it up with your synthetic division. Work your way along and you do get 0. So because you've got a remainder of 0, x minus this number, so x minus 3 is going to be a factor. So you can say it's x minus 3 times, and because that's x cubed, that'll be 2x squared plus 3x minus 9, just like that. Factorize that fully and you get the 3 brackets, set them all equal to 0, and you get the 3 values of x. You've got 3, 3 over 2, and negative 3. This example here, it was saying show that it's only got one real root. We did that the same way. We had to work out f of 1, f of negative 1, 2, negative 2, and so on. It works out that f of negative 1 would give you 0. So therefore, if you put a negative 1 here, you can say x take away the negative 1. In other words, x plus 1 would be a factor. Working your way along there, you can work out the coefficients of the other bracket, but you can say it'll be x plus 1 times by the x squared plus 2. From there, x equals negative 1's a root. That's what you were told. You had to show it was the only one. How do you do that? Well, this bracket would also equal 0, but there's no number that you can square and add 2 to get 0. Really, because if you rearrange this, you'd be taking the square root of a negative. And taking the square root of a negative, it breaks the entire world. You cannot do it. So you would say there are no real solutions for that one, meaning x minus 1 is the only real root. After that, we were out hunting down coefficients. A lot of the time, your polynomial, there will be numbers in front of your x to the power of 4, 3, 2, 1, 0, but sometimes you'll have a letter in their place. So this example here, we had p x squared, but we were given information that would allow us to work out this value of p. The way we did that was Well, if we know x plus 3 is a factor, we know we can divide it by x plus 3 and we'd get a remainder of 0. So set that up, work your way along. Just so happens that we don't get 0 though, we get 9p take away 27. But we know if this is a factor, this 9p take away 27 must be equal to 0. So set that equal to 0, add 27 to both sides, divide by 9, and p would equal 3. We had more examples like that. This one here, it was just mixing things up and going absolutely mental because it was showing us there were two unknowns. We had A and B. But it gave us two pieces of information. It told us x minus 2 is a factor, and they're spoiling us. They told us x plus 4 is also a factor. So divide this polynomial by x minus 2, this is what we get. And divide it by x plus 4, this is what we get. We end up knowing that the 8a add 2b add 4 is equal to 0, and this expression here is equal to 0. And because of that, we could then use simultaneous equations. Woohoo! From that, we can solve the simultaneous equations to get the values of a and b, which is what we were asked to find. After that, this example here is just another one saying that one root of this polynomial is x equals 1. Find k, and hence find the other roots. I gave you two methods of doing that. Remember, you could just go down the route of substitution, or you could use this nested form. Both ways work. However, I'd probably prefer method 2 because this then sets it up for working out the coefficients once you factorize later on. If you work out the value of k, that worked out to be 8, so you can just rewrite that bottom, not just the bottom line, rewrite all of that, replace k with 8, so obviously k add 1 would be 9. If you rewrite that, you could then factorize that fully because 1 out here is a root. X minus this number would be a factor. So x minus 1 is a factor, and we can factorize the rest of it. From there, factorize that fully. We've got x minus 1, x plus 2, x plus 7, and then we get the three values of x for solving that. After that, we're looking at functions from graphs. A lot of the time we will be given a graph and we'd have to work out the function, work out the equation. And to do that, we look at the places it crosses the x-axis. So this funky graph here, we can see it crosses at A, B, and C. Therefore, we know that the factors are going to be x minus a, x minus b, and x minus c. Remember, if you have the roots x equals a, x equals b, and x equals c, if you move the a to the other side or subtract a, it'll give us x minus a equals 0. It's kind of reversing what we did when we had the likes of a quadratic. If we had the quadratic x minus a, x minus b equals 0 and we solved it, we'd set each bracket equal to 0, and then we'd find the value of x. But in this case, we're just undoing that. So if we know the value, we just arrange that and then put it back into brackets so we can get the factors. From there though, the equation of the polynomial, we would have f of x equals, we multiply the factors together, but we also have to include this constant k. K is going to change the steepness because this graph you can draw it different ways. If I told you to draw this graph, but it's got to pass through A, B, and C, you could draw it multiple ways. So K is going to change the steepness of the curve. However, if you know another point, if you knew this point D, you could then substitute that into this equation along with A, B, and C, and that would let you work out the value of K. And that's what we did with some of these examples. When we had this lovely graph right here, we knew it crossed at -3 and 2. So we can say that it has roots at x equals -3 and x equals 2. Rearrange them, so add 3 to both sides, or take 2 from both sides. X add 3 is 0, x take 2 is 0. Therefore we get the two factors, x add 3 and x minus 2. Putting it back in, we know that the equation will be f of x equals k, x add 3, x minus 2. Again, we need this value k, but we can work that out using the other information. This graph crosses at 0 and -12, so we can substitute in 0 for x, -12 for y, or f of x, and we can work out the value of k. Once we've done that, we can substitute it back into this line here, and then multiply with the brackets, and that gives us the equation of this graph. We did the same thing with this example, although this was crossing at 1, 2, 3 places, so we had 3 roots. So 3 roots, set it up the same way, it's k times those 3 roots. Sub in a different point that you know, we know 0, 30, so sub in 0, 30, and you can find k. Again, you write that out in a line, multiply out your brackets. Very similar to the first example. This one here was slightly different though. Remember that you would have a root at -2 and you would have a root at 3. However, this 3 is a repeated root. The graph is going into 3 and it's also coming out of 3 as well. It's not just passing through. So that is known as a repeated root. So you'd have to write that down twice. Therefore, your factors, you would have an x plus 2 and x minus 3 and x minus 3 again. So always have a look to see if that is a turning point. If it is, then it's a repeated root. Apart from that, you did it the same way. Look for another point that the graph's going through. Here it was 2, -2, so you can sub that into this equation that you came up with to find the value of k. Sub it back in, and then multiply out your brackets, just the way you did in Nat 5. After that, we looked at curve sketching. We can graph different functions, and we can use our knowledge now of polynomials to help us sketch what a graph would look like. So with this example, we had to find the x and y intercepts. In other words, where it crosses the x-axis and the y-axis. We had to find the stationary points. We'll do that with differentiation. And then we had to sketch the graph. Obviously, it crosses the y-axis when x is 0. That's dead easy. Replace x with 0. We can get the point. Where it crosses the x-axis, though, is when y is 0. So this time, this polynomial here would be equal to 0. And this is where our knowledge of polynomials comes in. Oh, yes. So we'd have to then factorize this. And to do that, you need to set it up just with your L shape, and you need to work out the f of 1 or f of -1 and so on. In other words, replace x with 1 and -1, 2 and -2. Find out what is going to give you 0. If you do this, if you sub in 2, it does give you 0. And since the remainder is 0, you can say that x minus this number, so x minus 2 is a factor. So x minus 2 times 1x squared, add 1x, minus 6 would equal 0. Factorize that and you get the 2 points. Finding out the stationary points. Well, stationary points occur when dy by dx equals 0. Look back to differentiation. Look at that chapter. Differentiate, set it equal to 0. The stationary points occur when dy by dx equals 0. You find the values of x. Use the nature points. You all use the nature table, sorry. You always need the nature table to tell if it's a maximum or a minimum or a point of inflection. Remember though, it asks for the stationary points, so after you know the x values, sub them into the original equation to find out what y would be, and therefore you could get the actual points. And you can say if they're going to be a maximum or a minimum. After you do that, use your information where it crosses the x-axis, the y-axis, the maximum, the minimum, the turning points, and then you will join the points together. You should be able to tell what they are going to look like. Obviously, if that's a maximum, then that is going to be the highest turning point. The graph will be doing something like that. If that's a minimum turning point, the graph will be doing something like that. You know, from here to down here, it's going to pass through that point. So you should be able to say what it looks like. That is everything for the polynomials chapter. Try the review lesson. If there's anything you are unsure of, then look back at those individual lessons or look at this recap again. But try the review exercise in the Maths in Action book, page 113. Good luck with that. Any problems, let me know. But have fun. Bye.